Hello, everyone. It's 5 o'clock Swiss time, 5 p.m. Welcome all of you to today's talk in ISI's Game Changer series. I'm Joachim Wamsgans, Director for Astrophysics at ISI and your host today. ISI, International Space Science Institute in Bern, Switzerland, celebrates its 25th anniversary this year. For a quarter of a century, ISI has served the space science community by offering various tools for scientists to meet in Bern and jointly do science related to space missions. Currently, physical meetings in Bern are not possible, so we try to create a couple of new ways for scientists to collaborate, interact, and exchange information. This Game Changer series is one of these new tools where we look at missions that change the game in the space sciences. We started in late July and have had about a dozen talks on missions to planets, dwarf planets, comets, and the Sun itself, like Cassini, Juno, Rosetta, or Ulysses. Last week, we had a talk on Integral, starting the astrophysical cosmology missions. In case you missed some of our previous talks, they were recorded and can be viewed on the ISI website. Before I introduce the speaker, let's announce next week's talk. Tom Brown from the Space Science Institute in Baltimore will talk about the Hubble telescope from cosmological conflict to alien atmospheres. Let me now come to today's speaker, Anthony Brown. Anthony is an associate professor at Leiden Observatory and has been involved in the ESA Gaia mission since 1997. He currently chairs the Gaia Data Processing and Analysis Consortium, a team of over 400 European astronomers and IT specialists who are in charge of turning the raw measurements from the Gaia spacecraft into a three-dimensional map of over 1 billion stars in our home galaxy, the Milky Way. Anthony is very broadly interested in the astronomical research that can be done with the aid of Gaia data, from studies of our own solar system to understanding the formation history of the Milky Way. Anthony, the stage is yours on your talk, Gaia, the Dynamic Sky in 3D. Please.
Thanks, Joachim, for the invitation and also for the nice introduction. So I will be talking about the Gaia mission. I will give a very brief overview of the mission itself, but mainly spend time on motivating why we are doing Gaia, just to also address the non-astronomers in the audience. And then I'll show a few of the science highlights that have come out of Gaia DR2. And for the first part of the talk, I think the astronomers have to bear with me a little bit. It's probably all very familiar, but I think it's important to set the stage for the non-experts as well. So here on this first slide already you see an image, which is actually not a photograph of the full sky, which was made with the Gaia DR2 catalog. So the white color scale tells you how many stars there are in that part of the sky. So you very clearly recognize the plane of the Milky Way. This is the disk of the Milky Way in which we ourselves are sitting, and hence we get projected on the sky, the Milky Way. And you can also recognize the large and a small Magellanic Cloud. They are also observed by Gaia. And you see lots of dark patches, which are clouds of gas and dust that obstruct our view to stars in the background. In the bottom left, you see the actual spacecraft, Gaia, and a nice artist rendition. And Gaia is sitting out at the second Lagrange point, about 1.5 billion kilometers away from Earth, and still collecting observations. So to start with the motivation, why am I working on Gaia since 1997? That's a long time already, and of course this is familiar for everyone working on space missions, but there must be a good reason. And the reason is that we want to understand how our Milky Way came to be. So what we see here, of course, is a view from the inside, projected on the sky of the Milky Way. And if we were able to travel outside, we think it would look something like this. So this is an artist rendition of the Milky Way itself. You can see that it's a disk galaxy with prominent spiral arms, which we have very roughly mapped over the many past decades. And one of the things we want to do with Gaia is to really pin down, at least in the regions nearer to the sun, exactly what, for example, the spiral structure looks like. And you have to imagine that we are sitting here at about 30,000 light years away from the center of the galaxy, which is over here in the middle of the bar of the Milky Way. So once again, this is what we think the Milky Way looks like, and one of the goals of Gaia is to clear up this map and turn this in from an artist's rendition into actually a measured 3D structure. But the more important goal is to understand how the Milky Way was formed. Now, of course, there are plenty of theories of how galaxies form, and the most popular over the past decades or so has been the idea that galaxies form hierarchically, which means that they start out after the Big Bang. One starts out forming small units, dwarf galaxies, that then merge together in order to form the larger galaxies, to keep it simplistically speaking. So what I'm going to show now is a simulation of the formation of a galaxy like our own Milky Way. You see here the end state of the simulation, with on the left the distribution of the gas in this simulated galaxy, and on the right you see the distribution of the stars in the same simulation. Now, just after the Big Bang, things look like this. So there have been only a few smaller galaxies that have formed in the dense parts of the gas distribution, and it's these smaller galaxies that will start merging together in this simulation and gradually build up the galaxy that we will see at the end, which looks a lot like our own Milky Way galaxy. So I'll show the simulation now. So maybe just focus on the right-hand panel where you see the distribution of the stars, and notice how slowly in the middle the large galaxy is forming with spiral arms, etc. And then as we approach the end state, it starts to look more and more like the artist rendition that I showed before of our own Milky Way. So this is the end state, and I'll let the simulation run again. So to have another look at it. So as these galaxies fall in towards the center, you will notice that they are ripped apart basically by the tidal forces and the gravitational potential of the growing galaxy. And it's these sort of spaghetti strings that eventually then merge completely with the central galaxy. And in the end, it's very hard to recognize actually what the original building blocks of the Milky Way were. But the goal with Gaia is to try and find those for our own galaxy. Okay, so that's how we think our galaxy has formed. And the question is, can we find out the details of this with Gaia? Now, just to be clear, this is not just the astronomer's imagination in the computer. These events of smaller galaxies merging into larger ones also happen in nature. And there are many pictures of such events ongoing. And these are just two examples taken by, in fact, amateur astronomers. On the right, you see a disk galaxy edge on. And if you make a very long exposure, you see this beautiful string going around this galaxy. And that's exactly one of those dwarf galaxies that has been torn apart in the tidal field, in the gravitational potential of this galaxy. And it will slowly then merge over time with the galaxy itself. On the left, top left, you see another example of a very nice spiral galaxy. And again, if you take a long exposure, you notice that there's diffuse light, which is sitting well beyond the main structure of the galaxy. And if you make an n-body simulation of one of these smaller galaxies falling in, then you can actually very nicely reproduce this diffuse light in this simulation. Essentially, what you're seeing here in this diffuse light is the turnaround point of stars as they orbit around the galaxy itself. So this is just to demonstrate that this idea of hierarchical formation, there is very clear evidence for it in nature. But what we want to do is we want to find these building blocks of our own galaxy around, for our own Milky Way in order to reconstruct its formation history. Now here's another simulation. This I did together with colleagues in Mexico many years ago, and these simulations show 3 of those small galaxies that have been torn apart in the gravitational potential of the Milky Way. And this is what they would look like projected on the sky. And to first order, it looks like it should be very easily, it should be very easy to find these, because you can simply make a map of the sky and you can find all these remnants of these dwarf galaxies. However, this is just a small number of stars. If we add all the other stars to the Milky Way in the disk and in the bulge, then you get this picture, which is just the disk plus the bulge and not much else going on. Now, if you look carefully, you notice that here there's a little bit of extra yellow color compared to the same region on the other end of the sky. And indeed, that corresponds to one of these small dwarf galaxies that was torn apart in the gravitational potential. Now, this means, so the point I'm making is that in this simulation, which looks very boring, those other galaxies are actually included, but it's impossible now to recognize them on the sky simply because they're lost in the middle of the other stars. So what we want to do with Gaia is make a different kind of map, which is shown over here. And this is a map of the velocity of the stars as a function of the distance at which they are lying. So velocity here in kilometers per second. In this case, we're looking at the radial velocity of the stars, so whether they're moving towards us or away from us. And the distance down here is in kiloparsecs. Now, what you notice that most of the stars from the Milky Way are sitting very close to us and spread out over all kinds of velocities. But the most prominent thing you see in this picture is, again, these spaghetti trails, which are clear signs of these dwarf galaxies that are being torn apart in the gravitational potential of our own Milky Way. And the reason they are easily recognizable here is that these stars that are torn off from these dwarf galaxies tend to stay on the same orbit, or on very similar orbits, and that means that things like their energies and angular momenta are conserved and very similar, and that's why they also show concentrations in the space of velocity versus distance. So that means that we really need to know not just where stars are on the sky, but we really have to measure their distances as well as their motions in order to untangle things like the formation history of the Milky Way. Now that's symbolically indicated over here. So we just to summarize, we want to understand how did our Milky Way form. And in order to do that, we need to measure where stars are in space, not just on the sky. So we need their distances. That's symbolically indicated here by this map of the stars near the sun. And we need to measure their motions in order to, sorry, let me just pick up those, get rid of the phone. Sorry about that. Yeah, as I was saying, we also need to measure the motions of the stars, which is illustrated here with this other simulation of a dwarf galaxy being torn apart in the potential of this galaxy. And then finally, what we also measure with Gaia is the properties of the stars. So it's nice to, of course, to know the distances and the motions. That's very important information. But if we really want to do archaeology of the Milky Way, we need to be able to order things in time. And therefore, we need to know the ages of the stars, but we also want to know the compositions of the stars in order to identify the original building blocks that contributed to our own Milky Way. And this is symbolically indicated here by the Hertzsprung-Russell diagram. And so one of the important things that Gaia also does is measure these properties of the stars. Now, this is then a summary of the mission itself, the goals that we have in terms of the measurements we take. On the images on the right show again the spacecraft itself as it sits out in space, fully unfolded. And in the bottom right, you see an image of the payload of Gaia during its testing phase. And you see the two main mirrors. So Gaia carries two telescopes with which it's observing the sky. And down here in the bluish light is where you have all the detectors sitting. So Gaia carries about 100 CCD detectors on board with which you collect the measurements. So what is Gaia measuring? Astrometry and spectrophotometry for about 1 billion objects, well over 1 billion objects, as we'll see later. We also collect radial velocities for about 100 million objects. That means that we have the full 3D motions of the stars. And the Gaia survey itself is essentially complete out to 20th magnitude. So that's about 800,000 times or a million times fainter than what you can see with the naked eye. And the observing program itself is completely autonomous. So there's no input catalog or anything like that. Gaia just scans the skies, automatically detects point sources and measures them. And then because Gaia spins around its own symmetry axis every 6 hours, and by moving the spin axis around the direction to the sun, we can actually cover the whole sky in about a few months' time. And this means that stars are measured regularly over those 5 years with a quasi-regular time sampling, on average about 70 times. So Gaia is actually also very good for things like variability studies, of which we'll see examples later. Launch was in December 2013, and the 5 years of nominal missions operations are already over, so time really flies. So the nominal mission ended the middle of last year, and we are now in extended operations, and we have just been approved to continue until the end of 2022. And there is also indicative approval to continue for the next 3 years until 2025. And 2025 is more or less when we know that the mission will come to an end, because that's when we run out of fuel for the micropropulsion system, which is really the only lifetime limiting factor at the moment. Okay, so astrometry. So what is Gaia doing? It's in fact just measuring positions of stars on the sky, but by doing that regularly over time, you can actually figure out their distances and the motions. So the parallax of a star, which is illustrated in this animation, is measured by continuously looking at a particular target star and measuring its position with respect to background stars. And because our perspective on that star changes over the course of time, it looks like it's carrying out a sort of circular motion on the sky, but that's just a reflection of the fact, of course, that we are moving around in orbit around the sun. And if the star is very close to us, it makes a large circular motion. If you move it very far away, then this motion becomes much smaller. And it's exactly this motion that we try to measure in order to determine the distances to the star. So this is, in fact, the only geometric way we have of measuring distances without making assumptions about the properties of the stars themselves. The second component is of the astrometry is the proper motion that we measure. So there's a spelling error here, so it's a proper motion. And what you see here are two images of the same area of the sky, 50 years apart. And if you look at this configuration of stars, you can indeed tell that it's the same area on the sky. And next to this star, which is a so-called Barnard star, there's an arrow, and that star has significantly displaced over those 50 years. So all the other stars seem to be more or less stationary, but this particular star has really moved significantly. And of course, all stars actually move across the sky. This is a so-called proper motion, and it's just a reflection of the fact that stars are moving with respect to us, with respect to the sun. And Barnard star happens to be a star that is particularly close to us and also fast moving, and therefore you can quickly see that it's actually changed position over those 50 years. But with Gaia, we can do this for all these stars in this image and on the sky. Okay, this is what the sky would look like if your eyes were able to see parallax. So you would, and if the stars were stationary, then the only thing you would see is the fact that we are moving in orbit around the sun, and therefore it looks as if the stars are moving back and forth on the sky. And of course, the size of these little circles then tells you something about the distance to the stars. Now, if we add proper motion, we get the following picture. You can notice one star going very fast through the image. And you see that the star highlighted, it makes a sort of spiraling motions, which is the combination of this parallactic motion caused by our orbit around the sun and the motion of the star itself through space. And what we do with Gaia is in fact measure over the course of time the position of the star on the sky, and then and in fact we're trying to measure its position along this spiral as accurately as possible, and then we fit a model that then tells us what is the parallax and the proper motion of the star, thereby telling us something about the distance and its motion through space. Just to give you an actual example of what would happen if we were able to look, if we can speed up time and show how the sky actually changes because of proper motion. Then here's the Big Dipper in the northern sky. And if I set this in motion, you will see, first of all, the stars going back and forth. This is again the parallax, but of course also the constellation itself starts to distort. It's at some point not recognizable as the Big Dipper anymore. And that has to do with the fact that stars are moving through space and changing their position with respect to the sun. So just to illustrate that the skies are not stationary, but really dynamic. And with Gaia, we're really bringing this to life for all of the sky out to great depths. Okay, just one word on the precision that we attain with Gaia. So the most precise parallax measurements, where we try to measure this the angle of the circle that the star makes on the sky, so the size on the sky. The most precise parallax measurements that we hope to achieve are 10 microarc seconds. And just as a reminder, 1 arc second is 1/3600th of a degree. But if you turn that into radians, it's 5 millionths of a radian. So it's already a very tiny part of a circumference of a circle. But this translates, if you make some analogies, into 10% uncertainty in distance at the distance of our own galactic center. So that's really very impressive. 30,000 light years away, and you can still say where a star is to within 10% accuracy. The Barnard star that we saw before, we saw a picture 50 years apart showing the motion of the star. And in fact, at this precision, Gaia can measure the motion in 30 seconds. And the other analogy I like to make is that if you put a euro coin on the moon and your eyes were sharp enough to be able to see it from Earth, then you would have a resolution of 10 microarc seconds. So to give you a bit of an idea of how incredibly accurate the measurements are that we do with this spacecraft. Okay, so Gaia really represents an enormous step forward. Of course, we had an astrometry mission before, Hipparcos, which was launched in 1989, and the catalog came out in 1997. And what you see here is an illustration of the reach of Gaia. These are all stars for which the distances have been very accurately estimated with the Gaia DR2 catalog. So there's a little preview actually already. The sun is positioned over here, and you can see that we're covering a very large fraction of the disk of the Milky Way, and even the central bar has been mapped directly by measuring distances to stars. And if you can compare that with what Hipparcos did in the previous century, this was really accurately mapping a very small region around the sun, where most of the stars are that Hipparcos measured. So you can really see the enormous expansion in knowledge that we have of the structure and the motions of stars in our own Milky Way. Okay, here's just an illustration of Gaia measuring the sky. So it has 7 strips of CCDs that continuously scan the sky. And what you see here is how Gaia, over the course of about 1 minute, already measures of the order of 100,000 stars. So it has an enormous data collection rate. And of course, all of this data has to be turned in, all the raw telemetry has to be turned into a catalog that can be used by our astronomy colleagues. And that is done by a large team of scientists and engineers spread out over Europe, as Joachim mentioned at the beginning. So there's we've been going at this well over 15 years already. There's 100 institutes involved in Europe, 24 countries, and also ESA makes a very significant contribution to our data processing effort. And we have 6 data processing centers that are taking care of the various aspects of the data that Gaia collects. And just to show that there is real people behind this, this is a group picture of about half the members of the consortium that was taken a couple of years ago during a large meeting in Spain. And I always like to show this picture because it's important, of course, to stress that it's not me doing the data processing. It's really all this large team of excellent people in DPAC that are taking care of bringing these data releases to you. Okay, so now we have a look at Gaia DR2 and some of the results that came out. So this is just a summary in numbers of Gaia DR2. So we measured the position and brightness on the sky for almost 1.7 billion sources in this catalog. We actually have many more stars in the available in the Gaia or in our own databases, but they will be released later once the data quality is sufficiently good. But this is already a very impressive number. Now, the parallax in proper motion was measured for about 1.3 billion stars. So for the rest, we only have their positions on the sky. But for 1.3 billion stars, we know the parallax as well as the proper motion. And for the same amount of stars, Gaia is also measured, or well, we released in Gaia DR2 also the colors of the stars in a broad blue and red band. Later on, we will release much more detailed color information, which we are currently using to characterize the stars. However, even from this rough color and the parallax, you can already make very good estimates of the surface temperature of stars. So we have done that for about 160 million sources. And these temperatures are certainly not as accurate as you could do with spectroscopy, for example, but nobody has 160 million, and that's the power of Gaia. From those same data, colors combined with parallax information, you can also infer the amount of dust along the line of sight between us and the star for about 87 million sources. And also radius and luminosities were derived for stars for about 76 million of those cases. Now, this smaller circle over here is the radial velocities that were published as part of Gaia DR2. So Gaia also carries a spectroscope on board that takes medium resolution spectra, which we can use the Doppler effect to measure these radial velocities. And it's small compared to the rest of the catalog, but it's actually a very impressive survey on its own. 7 million radial velocities collected over the space of just 2 years. And this will become much, much more in the future. But even so, it's already the largest radial velocity survey that was ever undertaken. I mentioned that Gaia is measuring repeatedly over time the same stars, which means we can also measure brightness variations. So we also put out a catalog of variable stars. And this is at the moment about 500,000, and this will also increase very much in the future. And the other thing that Gaia does is that it measures objects in the solar system, particularly mainly asteroids. So anything that is point-like enough is measured by Gaia, and we'll get also very accurate astrometry for asteroids in the solar system. And in Gaia DR2, we released a sample of about 14,000 of solar system objects. And again, this will become much more in the future. We estimate of order 350 to 400,000 asteroids will be measured by the end of the mission. And one thing I should also point out about Gaia DR2 is that's the first time that we construct a astrometric reference frame in the optical based on direct measurements of the positions of quasars done by Gaia. At the times of Hipparcos, we had to align Hipparcos to the celestial reference frame defined in the radio with some intermediate steps. And here we can do this much more directly and also construct a much more dense optical reference frame based on these quasars and the rest of the catalog. So that's also a first for Gaia DR2. Okay. So just again a view of the sky a map of the night sky that you can make on the basis of these Gaia data. And I point out again that this is not an image, not a photograph. It's really all the sources in the catalog. We've put them in their correct position on the sky. And then the color, the whiter it becomes, the more stars you have per square degree. So for example, this dot over here is the globular cluster Omega Cen. It's not a star. So there's millions of stars, in fact, concentrated in, well, a few million stars concentrated in just that dot. Not all of them are measured by Gaia because they, in the very core of globular clusters, they're too dense for the onboard computing resources, but still you get excellent measurements in globular clusters. And this is a very nice illustration of the very high spatial resolution that Gaia attains over the sky. It's in fact comparable to the Hubble Space Telescope resolution in the images of that mission. One thing to note is that if you look closely, you see some faint streaks in the image, and this has to do with the way Gaia scans the sky. So in places where we scan a bit more often, we go a little bit deeper, so we see a few more stars, and this kind of imprint will always be there, but it's just a feature of the way we observe the sky. And the other thing to note is that in the galactic center region, you see something sticking out, and that is real. That is in fact the core of the so-called Sagittarius dwarf galaxy, which is a small galaxy in orbit around our own Milky Way. And we will come back to this galaxy later on in the talk. This is the same picture, but now in color. And now you don't see the distribution of the number of stars as in this image, but what you see is really the distribution of the light. And that gives a slightly different picture. But this is also a really beautiful view of the night sky. And it's in fact the main picture that we use as part of the Gaia data release to promote this. Okay. So now we go to a few of the science highlights from Gaia DR2. So there have been over 3,500 peer-reviewed papers based on this release since April 25, 2018. So obviously I'm not going to go through all of them. I really just want to highlight a few things that I think were important outcomes of the mission and where Gaia really makes a very big difference. We start in the solar system with a very interesting story about the navigation of the New Horizons mission from Pluto to Arrokoth, which is a Kuiper Belt object that was visited after the mission at Pluto was completed. And what you see here is a space telescope image showing this Kuiper Belt object here in the zoomed in part. And this is one of the images that they use to try and derive the orbit of this object very accurately in order to navigate New Horizons correctly towards this Kuiper Belt object. Now, they were not very certain about the astrometric calibration of their images because Gaia DR2 was not available at the time. So they asked us if they could have a pre-release version of the astrometry in order to help them navigate. We agreed to that, and so we provided for a patch of sky already a Gaia DR2 positions, proper motions, and parallaxes, and this was crucial in the correct navigation of this mission from Pluto to this Kuiper Belt object. Now, the other reason Gaia was important in this respect is that what they wanted to do before visiting this object is to measure its shape by using stellar occultations. In order to do that, you need to know very precisely where the occultation track is going to be on Earth in order to have successful measurements. And the shape measurements are important in order to see how things are with respect to spacecraft safety. For example, are there rings around the object? And of course, it also helps you in planning how to take pictures, etc., of the Kuiper Belt object itself. So the Gaia catalog was also used to make a very accurate prediction of an occultation track here over South America. And this shows the result of those occultation observations where the purple dots show the start and the end time of the observation, just lasting a few seconds. So this is when the star is hidden by the Kuiper Belt object. And you can very nicely see the outline of Arrokoth. And of course, if you think about the picture that was sent down eventually from the flyby, it beautifully corresponds to the outline that was seen partly with the aid of the very precise sky map that Gaia has produced. And in fact, this application of stellar occultations is one of the things that has gotten a real boost since the appearance of the Gaia data releases. And it's now possible to study objects such as Arrokoth at about 1 kilometer resolution just by using these very precise occultation measurements. And I think this to me as a non-solar system expert was a very surprising and nice application of Gaia data, and I think it's very cool that there's so much you can do just in the solar system already simply by producing a very accurate sky map. Okay, now we go to one of the things that Gaia, of course, is really very well known for, which is the properties of stars. By measuring their distances, we can know what is the absolute magnitude of the star. And we plot that here as a function of their color, a so-called Hertzsprung-Russell diagram. And the stars are not randomly distributed in this space, but they follow, most of them follow the so-called main sequence, which is indicative of a phase of the life of the star where it spends most of its time. So that's where you find most of the stars. And stars that evolve away end up, for example, on the giant branch, and eventually they end up down here and they become white dwarfs. So you can see all these features very beautifully outlined in this Hertzsprung-Russell diagram. Now, this is a diagram that was passed to me by Laurent Ayer, and he and his team in Geneva. There's one of the Gaia data processing centers there. They look, in fact, at how stars vary over the course of time in brightness, which is something you can do very well with Gaia. And if you then measure where the variable stars are in the HR diagram, you can see them concentrated in very specific spots on the HR diagram. And it turns out, in fact, that this broad range over here is the so-called instability strip, which is where the stars are in a phase where they tend to pulsate, and that means that they also vary in brightness. And you can see here the various types of variable stars that one can find in the HR diagram. And with Gaia, we expect to identify really many millions of these over the HR diagram. Now, one beautiful thing that they did is make use of the fact that Gaia is not only measuring how the stars vary in brightness, but also how the stars are varying in color. And this is illustrated in the next animation. I'll set that in motion. So it's the same HR diagram. And first, we show the places of some of the well-known types of variable stars. For example, the Cepheids, long-period variables, are Lyrae stars. And now you see how the stars that were measured with Gaia, how they vary not only in brightness, which is the vertical motion, but also very strongly in color. In particular, the long period variables, you see that they make very large excursions in changing their color. And it's the details of the behavior of this that tells us lots about the properties of these stars. And for example, for the Cepheids, of course, are very important because they are used to measure distances to other galaxies in the universe, and helped us establish, in fact, the distance scale of the universe. But these things need to be calibrated at least once in our own Milky Way. And this is done, of course, by measuring accurate parallaxes. So I think this is a very, very nice example of the work coming out of the Data Processing Center in Geneva. Okay, then we go to the next topic, which was a very popular application of the Gaia DR2 data, which is white dwarfs. And I mentioned before that white dwarfs, they are sitting down here, and they are in fact the end states of stars like our own sun. So the sun is sitting over here in its the phase of its life now on the main sequence. But in about 5 billion years or so, it will actually become a white dwarf, and it will end up as a very faint, hot little star, about the size of the Earth. And so these are extremely compact. They're similar in mass to the sun, but about the size of the Earth. So they're very interesting objects to study. And with Gaia, in fact, the census of white dwarfs around the sun has increased enormously. So what you see on the right hand, on the left at the top is all the known white dwarfs before Gaia DR2, and you can see that it follows a particular footprint on the sky, which is related to the Sloan Digital Sky Survey, where most of them were found. But then here is the situation after Gaia DR2. So the sky is essentially fully covered, and we have an enormously expanded census of these types of objects around the sun. And in fact, out to about 100 parsecs or so, we think we are more or less complete in identifying white dwarfs. Now on the right, you see a zoom in on the Hertzsprung-Russell diagram for white dwarfs, which showed which was published as part of the papers coming out with the release. And it showed a very surprising set of features, this split along the white dwarf sequence, as well as this branch sticking out here. Now, normally what we know from stellar evolution theory is that white dwarfs, they start here at the top left as relatively bright and hot. And because there's no nuclear fusion going on in these stars anymore, they just cool off over the course of time. And that means that they become fainter and also redder in color. And this split here was not expected. And probably it has to do with the fact that on the top, in both sequences here, you have white dwarfs that are of roughly 0.6 solar masses or so. But we think that there is a difference in the atmospheric composition. That seems to be the most likely explanation at the moment, that on the top you have pure hydrogen atmospheres surrounding the white dwarf. And at the bottom, these are hydrogen-helium mixed atmospheres. There have also been other explanations put forward, but that one seems the most likely. Now, the interesting branch to look at is this one, this Q branch over here. This led to a very nice Nature publication from the group at Warwick University. And what they considered is the effect that you get when white dwarfs cool over the course of time, is that their interiors start to crystallize. And the interiors of white dwarfs are made primarily of carbon and oxygen in different mixtures depending on the type of white dwarf. And here you see theoretical prediction. So this is the luminosity or the brightness of the white dwarf as a function of its temperature. And you would normally expect it simply to start in the top left, as I just said, and just cool down over the course of time. However, as it crystallizes, the crystallization itself releases extra heat. And this means that for a little while, the cooling down of the white dwarf is slowed down. And this means that they pile up in this along this sequence over here. And that's exactly identified with this Q branch in the observational plane. And so this is the first time we have direct empirical evidence of the crystallization of the interiors of white dwarfs. And of course, because it consists of carbon and oxygen, you can fantasize about huge diamonds in the sky. But I think this is a really very cool application. And it shows the power of having accurate distance measurements. I mean, it allows you in the end to actually peer deep into the interiors of these exotic objects, white dwarfs. Okay, then we go to another topic. And this is what I think is the most spectacular discovery that was done with the Gaia data, which is about the motions of stars in the Milky Way disk. This is schematically indicated over here. Normally stars are supposed to be simply in orbit around the Milky Way, more or less circular orbits. And they also go up and down a little bit with respect to the Milky Way plane. So they also show vertical oscillations in their motion. Now, what was done as part of a paper put out by Teresa Antosha and collaborators is to plot this vertical motion, so the speed at which they move in the vertical direction, as a function of their distance above or below the galactic plane, the disk of the Milky Way. Now, for a normal equilibrium Milky Way, you would expect there to be nothing spectacular in this diagram. It should just be a blob of stars. And that's almost what you see here, but they noticed, if you look closely, that there is a spiral feature in the distribution of these stars. So they're not entirely uniformly distributed, as you would expect naively, but they are sitting in this sort of spiral feature. And if you color code this distribution of stars by the speed at which they go around the Milky Way, the azimuthal velocity, then the spiral is even much more prominent. And so this was really unexpected and had not been predicted as something that we would see in the Milky Way disk. In fact, we were a little bit worried for a while that maybe there was a problem in the data processing, but that was clearly not the case. There's no way you can make a data processing error and produce this. This was further investigated by an Australian group who used the GALA survey. It's a large spectroscopic survey combined with the Gaia mission data to show that this spiral, which here was mapped in the neighborhood of the sun, in fact, if you study the spiral, how it behaves in various positions around the Milky Way at different radii and different locations in the disk, you always see this spiral. Also, if you look at stars of different age or different chemical composition, you always keep seeing it. So it really seems to be a disk-wide phenomenon. And what this points to is a Milky Way disk that is not in equilibrium. And this spiral is actually a very good example of the process of phase mixing, where the stars are brought out of equilibrium and they're now slowly mixing back together into an equilibrium configuration. And that manifests itself as one of these spirals in the space of velocity versus position. And this can really only be done since Gaia DR2 is available. This was not possible before Gaia, because you need really a very precise and dense sampling of phase space in order to do this. Now, what is the explanation of this? The most likely culprit is in fact this dwarf galaxy Sagittarius, of which we see the core here sticking out in the map made from Gaia DR2. And the idea is that this galaxy is actually interacting with the disk of our Milky Way and disturbing it, and thereby causing this disequilibrium. Now, this story has been expanded. So here what you see is a study by Ruiz Lara et al., where they looked at the color magnitude diagram for stars in the solar neighborhood, and they used the color magnitude diagram to actually reconstruct how the star formation history of the Milky Way, so how much stars formed as a function of time. And you do that by basically modeling this observed color magnitude diagram, and this is their model. But from the model, they actually can infer the rate at which stars were forming, which is the vertical axis, as a function of time. So here is the time just after the Big Bang, which is when the Milky Way was forming lots of stars, and that gradually decreased over the course of time, which is actually expected. But you notice that there is a few peaks happening in the star formation history itself. And it turns out that this dwarf galaxy that is going around the Milky Way, every time it crosses the disk, it seems to cause one of these peaks in the star formation history. So just to show that in terms of an animation of what is going on. So here you have the Sagittarius dwarf, and we'll set this in motion. Here you see this plot of the star formation history. So this is the first time it crosses the disk, and you see that there's a big peak in the formation, star formation rate. And every time it crosses the disk, you get one of these peaks, until we end up more or less at the present day situation, which is that it has recently crossed the Milky Way disk, and it's now sort of coming up behind the Milky Way center, which is why we see it in the map of Gaia DR2. Now, to show it more in a slightly more dynamic way, this is a simulation that was done by the Australian group. And it shows again the effect of Sagittarius, of this dwarf galaxy. So here it's coming in. You see the Milky Way from its edge on, and here from the top. And you can see how the Milky Way disk is really reacting very strongly to the fact that this small dwarf galaxy is caught into an orbit around the Milky Way. And now we're getting close to the present day. This was the last crossing, and this is where Sagittarius is sitting now. The sun is over here. And we think that this spiral is a manifestation of one of the last times that the Milky Way disk was disturbed again by this dwarf galaxy. Now, this disturbance, essentially what it does is it causes ripples in the disk of the Milky Way. And we see this also in the Gaia data, which show very complex behavior in terms of the motions of the stars, which cannot be explained by simple equilibrium models. You need to invoke a strong disturbance. And again, this dwarf galaxy seems to be a likely culprit. And it's also shown, this is a work that was done by Eloisa Poggio and collaborators, where they looked at the disk on a much larger scale. And we know already from past observations that the disk is not flat, but it is in fact warped. It has this shape, as you see in this model. And what they measured is in fact the rate at which this shape, the warp in the Milky Way disk, is actually precessing around the galactic center. So rotating around the galactic center. And you see here the data in terms of the projection of the motions of the stars in the vertical direction on the Milky Way disk. And here is a model with a warp that is actually precessing. And you see also a flat disk model, which clearly doesn't fit, and also a static warp model, which again doesn't fit. So we really need to have a precession. And one of the things is that one of the possible explanations is again that the interaction with the Sagittarius dwarf galaxy is inducing this precessing deformation of our own Milky Way disk. Okay. Oh yeah, this is also very nice. This is an animation that was done again based now on variable stars, and in particular the RR Lyrae stars. And for these stars, I'll set this in motion now. We first see a map of their distribution on the sky. These are all the RR Lyrae stars that were found with Gaia DR2. And for these particular stars, you can very accurately figure out their distance just by looking at the way they vary in brightness. And so you can turn this 2D map of the sky into a 3D distribution of the stars, and you see here very nicely highlighted the Sagittarius dwarf galaxy. So this is the core of the galaxy. These are all stars that have been stripped off before, sort of outlining very roughly the orbit. So again, the Sagittarius dwarf galaxy playing a prominent role here, and in this case, it's being traced with the aid of these variable stars coming out of this particular work that is done in Switzerland in the data processing. Okay, then the last topic, which was also, which is in fact what Gaia was built for, is to understand the formation history of the Milky Way better. And this is about the last time that our Milky Way underwent a really significant merger with another galaxy. So the Sagittarius dwarf galaxy is very small compared to the Milky Way. So although it's having an effect at the moment, ultimately it will not be a very significant merger. But the last one we experienced was about 10 billion years ago. And I'll just say something about how that was discovered. So here you see again a Hertzsprung-Russell diagram for about 4 million stars with very accurate distances from Gaia. But these are all the stars with these accurate distances. If you now concentrate only on stars that are moving at very high speeds with respect to the sun, then you get this HR diagram. So these are all stars that are moving at more than about 200 kilometers per second. And these very fast moving stars tend to be stars that are in the oldest component of our Milky Way galaxy, which is the halo, that is a spherical distribution of stars more or less surrounding the Milky Way disk. And the surprising thing was that the main sequence of the distribution of these stars is actually split into a blue and a red sequence. Again, this was something that was not predicted before. And these sequences were further investigated by Amina Helmi and her group in Groningen. And what they did is they looked at roughly a diagram of the energy of the star, which is the proxy is basically the dispersion of the velocities in the X and Z directions in the galactic coordinate system. And you plot that as a function of the azimuthal velocity of stars as they go around the sun. So stars at high azimuthal velocity and low dispersion are typically stars that are sitting in the disk of our Milky Way. And they concentrated on these stars here in this sort of bluish cloud, which are all stars that are, in fact, partly rotating in the other sense around our galaxy, and also have very large dispersion, so typical of halo populations, so part of the oldest parts of our galaxy. Now, looking at this plot reminded them, in fact, of a simulation that was done many years before Gaia was actually launched. And that is shown here on the right panel. And this simulation had, in fact, a dwarf galaxy coming in at a shallow angle into the Milky Way disk and then depositing its stars. And in particular, this feature over here at very large retrograde motions can also be identified in the actual data. And so the explanation for this split in the main sequence is, in fact, that this blue sequence corresponds to this dwarf galaxy that fell in, we think, about 10 billion years ago. And at the time, the Milky Way itself was smaller, and that meant that the galaxy that fell in was about a quarter the size of the Milky Way, so a very significant merger. And just to illustrate more or less what this looks like, this is the Milky Way, and here's this little dwarf galaxy, well, little, at the time, a quarter of the mass of the Milky Way. It's falling in. And it's coming in at an orbit that is retrograde with respect to the stars in the Milky Way that are going around clockwise. And if you pay attention, you will notice that the red stars tend to, on average, go around the other way. And that's how you can identify them in this diagram, where you plot the rotation velocity, the azimuthal velocity of the stars in function of their velocity dispersion. Okay, so that brings me to the end of the talk. So of course, the story isn't finished yet. Gaia is still collecting data. We are soon going to publish the next data release. This will be on December 3 at 12 CET exactly. And just to give a very quick, so you can find this overview page on the web. You can see the address over here. And there you can find much more information about the upcoming release. And in fact, the big step we're making in this release is that the precisions and the accuracies of the proper motions will go up by about a factor of 2. So this shows the proper motion uncertainty in milliarcseconds per year as a function of magnitude for Gaia DR2 and for Gaia EDR3. So the next upcoming release, it will look like this. So about a factor of 2 better. And you can also see the extrapolations to a 5 and 10-year period of data collection. So there's really much more to come, also in terms of all kinds of other data products that we still haven't put out. And those will come out in 2022. So let me stop here.
Thanks very much indeed. You have to multiply my clapping hands by about 260.
Good.
I have to catch my breath. Thanks very much for a very impressive talk on a very impressive mission. Now to the participants, there are 2 ways for you now to ask your questions or give your comments. You can either raise your hand in the participant list, and then it will be sorted here according to time, or you can write your question in the chat and then we will read it. In fact, there was already one question in the chat 5 minutes into your talk by Hans Zinnecker. Let me read this until more questions come in. So Hans asked, "Hi Anthony, I follow your talk from Santiago. I will ask my question how Gaia can inform us about the origin of OB associations and whether the new Gaia PM data, the ideas of Adrian Blau, your mentor, have to be modified, and if so, how?"
Yeah, well, Gaia will definitely inform us, is informing us about the about OB associations, and so far what has been done is really to improve the inventory of young stars in the solar neighborhood. So a PhD student of mine, Eleonora Zari, has done a thesis on identifying not only O and B stars, but in fact all young stars in the solar neighborhood and mapping their 3D distribution. And also the motions, but we still have to really get to the details of this. One thing that does come out of that is, for example, that Gould's belt, which has long been thought to be an entity that requires a particular explanation. From what we can tell, it looks like more that it's a chance configuration of associations in space. But I think this really untangling what went on with the associations in the solar neighborhood will take a little bit more time, because it's Gaia brings us much more data at a much larger level of detail, of course. But the drawback then is that it's also in some sense more difficult to understand. So that's still work to come.
Thanks a lot. I see a raised hand by Roger Bonnet. Saliba, our IT expert, can you please unmute Roger?
I think I am unmute. Is it right?
Yes.
Yes.
Okay. Thank you very much for a fascinating talk. It's really impressive. I really admire the results which you have obtained. In fact, I was a director of the science program at ESA when this mission was introduced in the program. And I was very surprised at that time that Gaia, as a second mission in astrometry, came so soon after Hipparcos. I was shocked, I must say, to see that all the efforts we had done on Hipparcos were suddenly disappearing in the potential that Gaia was offering. So I am very impressed, but I would like to ask you, what are the next missions in astrometry which you will consider as a child of Gaia?
Yeah, so on the European side, I think the most concrete proposal at the moment is to go for a version of Gaia in the near infrared. The reason is that then we can peer through the dust and really do a very dense sampling over a much larger volume in the Milky Way disk, which will really help a lot in understanding the Milky Way itself. And that would lead to the collection of many more sources, and also sits well in complement with many spectroscopic surveys that are going to be done in the infrared. And so a proposal for this was submitted for the voyage 2050, and also there's been actually already a study done of this mission in order to figure out which technology developments really are needed. And one of them is that if you want to do the same as Gaia, you need infrared detectors with time-delayed integration capability, and those are very hard to develop. And so we also have to look at other options of realizing the same mission concept, but then in the infrared. And then the other mission that is approved actually is in Japan. It's called Small Jasmine, and they will focus on astrometry of the central regions of the Milky Way, so a relatively small part of the sky. But it's very nice that Gaia finds a continuation that way in the not too distant future.
Thank you very much. This is a real good answer, and showing that Gaia is changing the game completely. If I had to vote for the next mission after Gaia, I will vote on the two that you mentioned. Thank you.
I'd be very happy if you vote yes.
Thank you. There are two questions in the chat related to each other. I'll read both of them. From Alison, she says, brilliant, thank you. Can you talk a bit about the Sagittarius A proper motion study? And a question by Bernard Foying. Thanks for great talk. Did you have specific results on galactic center?
On the galactic center, we don't have specific results because we can't see the galactic center, right? It's Gaia is an optical mission, so it's obscured. We can, of course, say a lot more about things like the bulge and the bar of the Milky Way, where for example, this overview plot that I showed of the reach of Gaia is actually from work that was part of which is really studying the bar of the Milky Way directly with Gaia data. But the galactic center itself, unfortunately, we cannot see.
Question from Bruno Marine. Great talk, Anthony. Do you have an idea of the typical amount of data used by the average Gaia paper compared to the size of the full catalog?
The typical amount of data is relatively small. So there's of course a lot of papers that simply go to the Gaia catalog to look up the basic properties of a star. What's the parallax, proper motion, brightness, etc. So most of the papers, I would say, use hundreds of stars or something like that, maybe. But of course, there's also a very substantial amount that use much larger samples. But the fact that it's now so easy to just look up the parallax of a star or its proper motion, I mean, that is really the power of Gaia. You never have to worry again anymore. You just, if you want to know something about your star, you go to the Gaia catalog and it's there.
There's a raised hand again by Elena Fedulova. Now can you unmute her, Saliba? Yes, please, Elena.
Yes, can you hear me?
Yep.
Yes.
Hello, great talk. It was really incredible to see this result. Thank you very much, Anthony. And also thank you for spending the time to explain the results to non-astronomers. So I am not an astronomer, I actually work in a scientific journal. And I do have a follow-up question. I just didn't understand something that you said about the split in the diagram that showed the white dwarfs when you were speaking about cooling and crystallization.
Yeah, let's go back to that slide, maybe just to, yeah, here, yes.
Yeah, and you said that the most probable reason is this. Is that what you said? That it's not certain yet?
No, that was so the crystallization is clear, I think, from the modeling. So this, and I mean, this is something that was predicted, in fact, 50 years ago, and now for the first time we have really solid empirical evidence. What was not entirely clear yet was this particular split, which is not related to crystallization. That's this feature over here, but the split between A and B. One of the first explanations was that maybe you have white dwarfs that are actually merging together and thereby creating a different sequence. Another explanation was the fact that there is a specific change in the relation between the initial mass of a star and its white dwarf mass, which could lead to this feature. But most likely it has to do with the atmospheric composition of the white dwarf. So if you have pure hydrogen atmosphere, the colors and the spectra are a bit different from when there is a little bit of helium added to it. And if you're not careful about how you interpret that, you might, for example, misinterpret the B sequence as a place where you have a more massive white dwarfs, but they could basically be the same mass, but just with a slightly different atmosphere. I hope this is somewhat clear. Yeah, right. Thank you very much. And my question was, will data from Gaia shed more light on this? Like, will there be a certain answer from the Gaia data on this? Maybe not from the Gaia data itself. I think this requires a combination of maybe a bit more follow-up observations with other instruments, like taking more spectra of these white dwarfs, and also theoretical modeling to see whether, for example, just the atmospheric composition is sufficient to explain what we see in the observations. But of course, for Gaia data in the future will become even more precise. So hopefully we can see even more detail in this sequence. And that should, again, give us clues about what's going on. Right, I see. Thank you very much. Yeah, sounds like
a lot of questions still in the chat. Maybe you can just give short answers so that we can address a few more. Megan Russell asked, how was the extrapolation of the increased accuracy to 10 years carried out? Last slide.
That's an extrapolation from the performance that we have now in EDR3. And you just, the EDR3 is based on 34 months of data. The 10 years is 120 months. And that gives you the increase in signal to noise and also the increase in the baseline for proper motions. And that allows you to make the extrapolation.
Thanks. Alan asks, what about astrometry to detect exoplanets?
Yeah, that's a good question. So the next release, Gaia DR3, so not the early, but the full DR3 is in 2022. And then we will put out a catalog of binary stars already based on deviations in the astrometry. And of course, the same principle can be applied to exoplanets, but that is probably only possible in Gaia DR4. Because that requires that we have the individual measurements of the astrometry, the calibration thereof under extremely good control. And so we are trying to run our exoplanet pipelines at the moment, but it's not clear that we will have a result for DR3, but for DR4, it's definitely planned.
Then there's a question from Priscilla. What value do you suggest use for the definition of the local standard of rest in reference to stars within about 300 parsec?
I don't really have an answer to that. It's not because nobody is looking at it, but I haven't followed that particular topic.
And we have two questions from my co-directors at ISI, one from Rudy van Steiger. Gaia maps only visible stars, obviously. Now we learned in introductory astronomy that galaxy rotation curves are constant, indicating the presence of dark matter increasing linearly with distance from galactic center. Can Gaia, by mapping stars orbiting the galaxy, say something more about the distribution of dark matter or even its nature?
Yes, so of course we infer the presence of dark matter by looking at the motions of stars and then seeing that the mass that we need to explain those motions in an equilibrium system is much larger than what we can see. So with Gaia, we can definitely do a lot more on mapping the details of the dark matter, and there have been several works in the literature already. And the other thing that you can do with Gaia is because you know how stars are moving through the Milky Way, in particular in the halo of our galaxy, you can also try to fine-tune the direct detection experiments by making sure they're looking in the right direction at the right time of year, based on how we know the stars are moving in our own galaxy.
Thanks. Tilman Spohn, our executive director at ISI, asks, when you spoke about 300,000 objects in the asteroid belt, you were actually including multiple observations of the same objects too?
Yes, so all those objects will, just like the stars, be observed multiple times. The number of times is going to be a little bit different depending on the particular orbit and how Gaia scans the sky, but comparable to the stars. And for each individual observation at the moment in Gaia DR2, for example, we are already down to milli-arcsecond accuracies. So that means that we have, for example, if you look at the quality of the orbits of these of some of these asteroids, there are cases where just the 2 years of data from which Gaia DR2 was produced allows you to get a better orbit than based on many decades of ground-based observations. So Gaia will really be very powerful in studying the solar system in that sense, also because we are also collecting colors of the asteroids, so very low resolution spectrophotometry, and a sample of that will be released with the DR3 as well.
Thanks. Thomas Müller asks, would interstellar visitors in our solar system like Oumuamua be automatically recognized by Gaia?
No, we wouldn't. You know, if we get lucky, we could in principle see it, and we would probably pick it up as what looks like maybe an asteroid, but maybe has only one observation or only a few. But it will be very hard, I think, to tell. I think we did look in our data whether Oumuamua or Borisov were actually seen by Gaia, but I think they were just missed and got unlucky. So not likely to happen.
Thanks. Sorry. 3 more last questions, again related to dark matter. Are there results on dark matter density in the galactic disk in the solar vicinity thanks to Gaia?
Yes, there have been several works that model the velocity distribution of the stars to understand what the dark matter density is. I don't know the results really off the top of my head, but one of the papers that comes to mind is by Wittmark and collaborators. They have done quite some work on the dark matter in the disk.
Roland Boninsenia asks, shall it be possible, knowing precise positions and proper motions of so much stars thanks to Gaia, to predict possible microlensing events between foreground stars lensed by nearby stars?
Yes, that has in fact been done. For example, the group in Heidelberg has put out a paper where they make such predictions, and where there were several events that are in fact ongoing at the moment, and they're trying to follow them up with other telescopes in order to get a better mapping of the event itself. But yeah, that's an application that has been used by a number of groups already.
In fact, if I may add, it was my PhD student, Jonas Klüter, who did most of the work. And these are astrometric microlensing events where you can see the background, the solar star moving in a little ellipse. And it's really very exciting to predict these events.
Yes, indeed.
Last question by Florence Libot. Hi, in the next release, will there be a better characterization for variable stars? I mean, the indication of the type of variability?
Yes, so that's not coming up in December, so we will not add new variable stars then, but in 2022. And the aim is to go for a sample of the order of 7 to 10 million variable stars with an expanded number of types that we are classifying. So it will be of the order of 20 if you count all the subtypes as well. I mean, this typing of variable stars was already done for Gaia DR2 for a limited set of classes, and that will be expanded then for the next for DR3 in 2022.
Okay, thank you. I think we should get to an end. Before we thank Anthony again, let me announce next week's talk again. Tom Brown from the Space Telescope Science Institute will talk about the Hubble telescope from cosmological conflict to alien atmospheres. Now I'd like to ask Saliba to unmute many participants so that we can really give a big hand to Anthony for a wonderful talk with very many scientific, exciting results and very inspiring results. Thanks again, Anthony. Wonderful.
My pleasure.